Hey guys, this is just a video of me explaining C and D. I told you I'd finish this out for you all. I tried to do it in sixth period, but something happened with the recording, so no worries there. Looking at C, a large clock has actually, I'm not sure if I finished this one. I think we got through. I don't know if I multiplied it or you all multiplied it and we got the answer. But we should be at, if we're putting it all in the calculator, .73. So 3.73, and that would be revolutions or rotations per second. And it looks like it's 735. Sorry. Round to the nearest third. Revolutions per second. So just wanted to clarify that. Okay. Next thing is C. A large clock has a second hand traveling at 2.5 inches per second. Find the length of the second hand. So if we have our formula, V is equal to omega R. And if we find the length of the second hand, so we all know a second hand on a clock rotates, right? And it's not talking about like the first second. It's not talking like first, second, third. It's talking the second hand, as in 1 second, 2 seconds, 3 seconds. So the second hand, we know it travels around, and it's wanting to find the length of that. So that's going to be our radius. Okay, that's going to be the radius. If we want to find the length of the second hand, it's going to be the radius. So we isolate the r by dividing both sides by omega. And we find that radius is equal to the linear velocity over the angular velocity. So radius is equal to linear velocity over angular velocity. So the linear velocity, if we're looking at this, it travels at 2.5 inches per second. So we would write that like this: 2.5 inches per 1 second. And then we put this over the angular velocity. Now this can kind of trip students up because it gives nothing besides the linear velocity, but this is where common sense is going to have to step into the problem, and you should know a little bit about a second. How many seconds are in 1 minute? So if you can imagine a clock, right, and the second hand starts here, how long does it take the second hand to get all the way around? Because that would be its angular velocity, or omega in this case. So it takes, one revolution of the second hand is actually 60 seconds. So again, that's not given to you in the problem. It's just, that's a, kind of logical for you to understand that a clock, it takes 60 seconds for the second hand to do one revolution. So this is the speed at which it's traveling, 2.5 inches per second. So got a pretty good sized clock here. If it's traveling 2.5 inches, you can imagine 2.5 inches per 1 Mississippi, 2 Mississippi. So it's a pretty large clock, and that's the key word there, that it is large. So then we just do some math from here. We keep, change, flip this. So we change this, we flip it up, 60 seconds over 1 rev. And then that kind of eliminates this right here because we've now flipped it up. So we have our seconds. Seconds are taken care of. That's taken care of right there. And inches is what we want. That's a linear unit. But we need to get rid of this rev. So the way we get rid of the rev is just to multiply all of this by 1 rev over 2 pi. And I know some of you may be thinking, well, 2 pi, 2 pi is technically, wouldn't that be, wouldn't the radian be there? And that would be true, okay? There is technically a radian there. And you may say, well, there's no cancellation of the radian, but I will remind you of the note up here. Radian is measured in distance per radian. So it should be in inches per radian, so that's why R is still there. It wouldn't cancel because radius is technically measured in distance per radian, but we never include the radian unit. So from there we get our calculators, and we just type in 2.5 times 60 equals that, and then divided by the revs cancel. I just want to make sure I'm good here. So 2.5 times 160 divided by 2 pi. Comes out to be 23.873, and that's inches. And we know it's inches, that's traveling inches, so we're going to keep it in inches here. So again, if the second hand, you can imagine how large this clock is if this is almost 2 foot. So 23 inches, almost 2 foot, so it's a pretty big clock. All right, that's C. Jumping down here to D, 2 gears are connected by a belt. The large gear has a radius of 6 inches, while the small gear has a radius of 3. If a point on the small gear travels at 16 revolutions per minute, find the angular velocity of the large gear. Now, gears, you would have to think, I think the best way to connect gears to students would be to think about a bike. The chain, it's on gears, especially if you have a mountain bike. We say, hey, switch gears. And when you switch gears, the chain jumps from one gear to the next gear. So that's what we mean by saying, hey, switch gears. So that's something that kids are kind of familiar with in how the chain goes up and down on the bike. So we're switching gears. So gears it's going to be circular, and it could have some teeth on it, right? Just like to hold the chain and stuff. But let's make this we'll make this our small one. Our small gear has a radius of 3, and we'll make our larger one here. And it has a radius of 6. Now I know, obviously not drawn to scale. And they're connected by a belt. Okay, so here's the gears. So it's kind of connected here by this belt that's moving around. Okay, kind of going in this motion here. Now, if you're looking at this problem, okay, here's what it says. The large gear has a radius of 6. It has a point here. At some point on the small gear, it's traveling at 16 RPMs. So, here's something kind of unique about this problem that really jumps off the some of you may see from the very beginning. If this is the small one, and it takes 3. And a small one with a radius of 3, and it takes 16 revolutions per minute that it travels around this. Some of you can kind of look at this and say, hey, this right here is double the size, exactly double the size of this gear. So if it travels on this gear at 16 revolutions per minute, then it should travel at what? At any point on here, it should travel at what? Well, this is where it gets like a lot of people want to double it and say, oh, it's 32. And that would be wrong. And if you think about this logically, it's going to get around the smaller gear much faster than it gets around the larger gear. Think about if I drew a small circle in the room, I could get around that circle pretty quick. But if I drew a big circle in the room, getting around that would take me much longer. Since it's double the radius, it actually takes double the time to get it around. So it would actually be 8 revolutions per minute. And that is the answer, 8 revolutions per minute. Now, that's all nice and easy, and you're like, okay, hey, that's simple. Put that on the test, and we're in good shape, right? Just double it, and we're in great shape, Mr. iPod. But as you all know, it's sometimes it's not as nice, and the numbers aren't as smooth. And I'm looking right now. I just want to take a look. I'm taking a look at my laptop real quick. Okay, I just wanted to take a look at my laptop because I wasn't for sure if a particular problem like this was on the test or not. So I didn't know if this exact question was. I couldn't remember from last year. But obviously it's easy if you look at it this way and say, hey, it's double, so it's going to be, obviously take double the time. So that would be, if it gets around that 16, it's half, it's going to be double it. So 8 revolutions per minute. But again, that's the logic behind the problem. Let's look at the algebra behind the problem. So we know our formula is V equals omega times radius. And notice we have two wheels here, so we actually have 2 because we have 2 radiuses. We have 2 angular velocity, and we can have linear velocity. So we actually need 2. We need 2 formulas. So this is for we can say this is for the small, and we can say this is for the large. Small gear, large gear. So the small gear, let's label it like omega sub s and radius sub s, and we'll name this omega large sub L and radius sub L. So we're just kind of giving it some units because we're obviously about to we want to be able to tell the difference in these. Now here's the cool thing about math. V equals this and V equals this. So anytime these two things, if you have something that equals something, you can put those two things together. So we're going to actually rewrite this like this. Omega sub s times radius sub s is equal to omega sub L radius sub L. Since V equals this and V equals this, we can set those equal to each other. Now, we know some things about some of this right here. We know the radius of the small is 3. We know the radius of the large is 6. And then what does it give us here? A point on the small gear travels at 16 revolutions per minute. So revolutions is an angle. Angle over time would be angular velocity. So the small gear has an angular velocity of 16. And it says find the angular velocity of the large. Well, notice that's what we have left. So we're going to use some just basic algebra here and figure it out. So we want to isolate the omega sub L. So divide both sides here by 6. Divide this by 6. That's 16 times 3 is 48. 48 divided by 6, you guessed it, 8. So it the algebra backs up the logic of this problem. So there we go. That is that. Just wanted to finish that off for you all so you kind of knew how to do those last two problems. I did add the homework. I didn't mention this to you all, but I did add the homework solutions to Canvas under Files. I sent you a message, but just in case you don't read that, but you listen to this, probably not likely that happens. But I'm sure you'll read that and not watch this. But just wanted to give you these two problems. Hey, you guys have a great Labor Day weekend, and I'll see you guys on Tuesday.